Alright, so today's video is going to talk about how we determine the location of electrons in an atom. And essentially what we're going to be covering are two fundamental skills regarding electron configuration and orbital notation. Now both of these skills require knowledge of quantum numbers before you continue. So those involve knowing about energy levels, sublevels, orbitals, spin, and all the requisite numbers that go along with those. So make sure you study those up before you continue on. Now in order to determine the location of electrons, we are going to deal with orbital notation and electron configuration. So electron configuration is the quickest and most straightforward of the two types of notation, but it doesn't really give us a full and detailed story as much as orbital notation does. But orbital notation is much more time consuming. So electron configuration only really tells us energy levels and sublevels and tells us total number of electrons in each sublevel. Orbital notation deals with pictures. So we're seeing the spin of each electron, it broken down all the way into the specific orbital, where we then see half-filled, unfilled, and fully filled orbitals. So a lot more detail than electron configuration gives us. Now, we're going to start with electron configuration from the standpoint that using electron configuration helps you to solve problems involving orbital notation. And the way we begin electron configuration is with these two images. The one on our left is our diagonal rule, and the one on the right is our periodic table. So the periodic table actually tells us a lot more than simply atomic symbols, atomic masses, atomic number, and so on. It tells us a great deal, especially about electron configuration. But my electron configuration tool of choice is the diagonal rule. Essentially what you do is you write this pyramid out, starting with your first energy level. That's what all these numbers represent, are energy levels. And the letters next to it represent sublevels. So the S sublevel begins in the first energy level, P begins in the second, D in the third, and so on and so forth. So essentially you write that down and continue all the way to the seventh. Now you follow down, and I tell my students that this involves slides, so I slide down in diagonal patterns, dropping electrons off as I go. So I keep sliding down, dropping off electrons until I'm all out. Now the S's hold 2 electrons, the P's hold 6, the D's hold 10, and the F's hold 14. We really don't worry much about these over here. They're more theoretical, and electrons don't occupy these areas permanently. Now for simpler elements, using the periodic table can be easier. So just like the diagonal rule, you determine the number of electrons in your element and drop electrons off as you go. So we have the periodic table broken up into specific blocks, and those blocks correspond to how many electrons fit in each sublevel. So the S block is 2 columns wide, P block is 6 columns wide, D block is 10 columns wide, and F block is 14. So each box represents a place that you can drop off electrons. So if I'm looking here at this element, which happens to be nitrogen, I know that there are going to be a certain number of electrons here, and I just keep dropping them off until I reach my destination. So I drop off 2 electrons in the first energy level, first sublevel, move down to 2s. We know that holds 2 electrons, and the arrow tells me to move all the way to the right, and I drop off my remaining 3 electrons in the P sublevel. So I count over 1, 2, 3, and that's how I get my total number up here. So nitrogen has 7 electrons in it. Adding these up should reflect my total electrons in my atom. Now, to give us an example, we're going to look at germanium. Germanium happens to sit right here in the 4p2 range. So Say hello to germanium. Now I'm going to use the diagonal rule in this case. So we know we have 32 electrons. So I draw my slide and I drop off electrons. So again, this has 2, this can hold 6, 10, and 14. So I dropped off my first 2 of my 32. I drop off my next 2. I drop off 6 in P, another 2 in S, and I just keep going down the slide until I'm all out of electrons. So I've dealt with 12, 18, 20, so 3P6, 4S2. I come down here, 3D10. So now I've dealt with 30 electrons, and now my last 2 go into 4P2. Now you can use your periodic table knowledge to verify that your electron configuration is correct. So we see that germanium is in the 4th energy level, so that must be your outermost energy level. We see 4 as our highest. And then we see that we are 1, 2, 3, 4 columns over. We're skipping the D block section. And that verifies that we have 2 or 4 electrons in the outer shell. So we can reasonably assume that our electron configuration is correct. Now we can use this knowledge to help us with orbital notation. And you can see here how it's drawn with pictures. Now these go into the use of 3 different rules. The Aufbau principle says every electron fills the lowest energy level first before going into the next energy level. Hund's rule says that if we have multiple orbitals that we're filling in that sublevel, you put in 1 electron in each first, so you're basically balancing out the energy and the charge before you start doubling up. And then the Pauli exclusion principle says no 2 electrons have the same quantum numbers. So essentially no 2 electrons are going to have the same spin because they're going to want to repel and go opposite of one another. So we see here each box represents an orbital. So this box right here is 1 orbital. These arrows represent an individual, an electron. So each arrow is an electron. We see here that fluorine has 9 total electrons, 2 in the first energy level, first sublevel, 2 in the second, 2s, and then 5 in the 2p. Now to see this in action, I want to give you guys an example using phosphorus. So phosphorus, what we do is we first want to write out our electron configuration. So again, I'm going to make a little tree diagram, and knowing that I have just 15 electrons, I'm going to make it short. And then I write 2p here, 3p here. So I have 15 electrons, and I'm going to drop them off. 1s2, 2s2, 2p6, so I'm at 10, 3s2, I'm at 12, and now I drop my last 3 off in 3p3. So I use this as my guide for drawing my orbitals. So now I write a line, so they're either orbitals are represented as lines or boxes, right? 1s2, put my first electron here with an upspin, always start with an upspin, and then the next one with a downspin. Moving on up, we have 2s, start with upspin, downspin, noticing we're filling the lowest levels first, so we're abiding by the Aufbau principle, and then we put 1 in before we put the second according to Hund's rule. Now we know in 2p, we have 3 orbitals, so we put in 1 each, abiding by Hund's rule, and then fill it going down. Moving on up, 3s, 2, and our last energy level is the 3p sublevel. So we have 3 electrons here, they all go up. So what this tells us is that all of these energy levels and sublevels below are full. Except when we get to the third energy level, we have 3 half-filled orbitals. So if you're ever asked a question or need to figure this out, orbital notation gives you a better idea about specific orbitals. So I hope you found this video helpful. It kind of doesn't go into any exceptions or noble gas configurations, but it should help to clarify your understanding of orbital notation and electron configuration.